Today's class, I wanted to move on from the work we were doing on random processes, random number generation, Monte Carlo calculations. Remember, we looked at things like Brownian motion, radioactivity, things like heat capacity and magnetism. We're going to move on from that to look at data. We're going to be looking at data to learn from the data, to try and interpret the data. And specifically, over the next few classes, we're going to be performing fits to the data with a model for the data. So that's the work over the next few classes. And today's class will focus on a linear fit to data. We'll look at some famous linear fit problems. We'll write our own code for a linear fit to data so we can get an idea of how it works. And we'll also introduce library functions for fits to data. The linear fits that we'll look at in today's class, one really famous linear fit to data is the fit that was first done by Hubble to data on the distance and velocity of galaxies that expose the expansion of the universe. So that was a really famous uh, fit to a straight line. Another one is, which was basically originally done by hand and done by Kepler, was fit to orbits of planets. You can fit to orbits, periods of moons around planets. You can fit to orbits of stars in galaxies. And in that way, you can learn about the mass of a planet. You can learn about the mass of the sun or stars. You can learn about the existence of dark matter. So those two are very famous, important least square fits to straight lines, linear fits. Okay, so I'm going to use the example of the expanding universe and Hubble's fit for today's class. So I just wanted to introduce a bit of background for that. I always feel slightly awkward talking about astronomy here because I'm not an astronomer and some of you are astronomers, so I've got to be really careful. But I just got a couple of slides to introduce the data behind the discovery of actually both galaxies and the fact that the galaxies are all moving away from one another. The universe is expanding, and how we see that in the data, how we extracted that, learned that from the data, how Hubble learned, extracted that. So it started with these stars that are called separate variables. As best I know, these stars are pulsating stars. So their brightness varies with time, changes with time. Maybe it's over periods of from days to, hundreds of days. So they pulsate with time. And I think they're pulsating just because they're at a certain rather special stage of their lifetime. Most stars spend their time burning hydrogen, but then towards the end of their life, they start burning the products of the burning of hydrogen. So they're burned through helium and carbon and other elements. And they're at a particular stage where they're burning helium. And the pulsating is really a pulsating of the amount of helium and the opacity of the helium, causing a pulsating in the brightness of the star. And so it's not that they're perhaps so much special stars, they're special stars in the sense of their special lifetime in their existence. So Hubble actually first demonstrated the existence of galaxies through these particular types of stars because there's they are known in our galaxy. Maybe there's dozens of them known in our galaxy. But he was also looking at spiral nebulae, trying to understand what they were. There was a big question at the time of whether they were in the galaxy or outside the galaxy. And they contain these Cepheid variables, and he was able to determine that those spiral nebulae are actually galaxies outside our own galaxy, the Milky Way. So that was a big breakthrough, that there were galaxies beyond that galaxy. Um, he built on that to look at the relationship between the distance to these galaxies and the motion of the galaxies, whether they were moving towards us or some moving away from us, and what the speeds were of their receding or approaching motion. So he used the Cepheid variables for those measurements. Basically, they're kind of like a candle, a known candle or a standard candle. You can determine the distance to these Cepheid variables based on their brightness. You can determine their motion with respect to us, whether they're approaching or receding from us and how fast, based on the Doppler shifts of their light. From those sort of proxies for their distance away from us and their speed traveling with respect to us, we can look at the distance speed relationship. So that's what he did for the first time. So he made this graph, made this plot of the velocity of galaxies versus the distance of these galaxies. And he found that all the galaxies were receding from us. And they were receding from us in a particular way, that if they were closer to us, they were receding less. If they're further from us, they're receding more. And that's characteristic of a universe that's just overall expanding. Everything's get further away from everything else. And if something's further away from you, it's receding faster from you. That's the characteristic of an expanding universe. That's a signature of an expanding universe. And that came out of these Cepheid variables. So it was a big deal because it was the first evidence for a expanding universe rather than just a steady state, stable universe. So it was an expanding universe, and it was a big hint for there being a Big Bang, which was the start of the universe. So that was a big event. He described his data with a law. We call it now Hubble's law. It just reflects that the recession velocities of the galaxies is in proportion to the distances to the galaxies. So if we're going to call those distances to the galaxies d, that the recession velocity is v, then Hubble's law just says that v, the recession velocity, is proportional to the distance to the galaxy, and the proportionality constant we now call Hubble constant, h naught here. So that's Hubble's law. By determining these distances to the galaxies, again, using this proxy of the brightness of the Cepheid variables, and the velocity of the galaxies, also using a proxy, basically the color or the redshift of the light from the galaxies, you can determine the Hubble constant, the constant in this relationship between the motion and the distance. And that comes out to be in these units here, 70 kilometers per second per megaparsec. So this is a unit for non-astronomers. This is the unit that Hubble constant is often quoted in. I presume because it's kind of convenient for the measurements that went into this unit. So it's the recession velocity, 70 kilometers per second per megaparsec distance from us. So it specifically means that supposing you're a galaxy that is 1 megaparsec away from us, Earth, then we would see that galaxy receding at 70 kilometers a second from us. If you're a galaxy at 10 megaparsecs from us, then we would see you receding at a velocity of 700 kilometers per second. So it's just reflecting how the recession velocity is scaling with the distance to the galaxy. Andromeda is about 1 megaparsec away from us, and so it is receding at about 70 kilometers a second from us. The units of the Hubble constant are inverse time, right? You've got a velocity, say meters per second, divided by a distance, meters. And so the units are meters cancel out in the numerator and denominator, and you've got units of inverse time. So the inverse of the Hubble constant is a time, and that's the age of the universe, assuming that this expansion has been going on at a constant rate. It's not been accelerating or decelerating since the Big Bang that produced the universe. So if you take the inverse of the Hubble constant, this 70 kilometers per second per megaparsec, and you put it, it is a time, although that's a funny combination of units. If you put it in units of time, in billion units of billions of years, it's 14 billion years ago. Okay. This is just to show his data, his straight line fit to the data, and how he extracted the fact that the galaxies are receding from us in a way that's in proportion to their distance from us, and how he extracted his Hubble constant, how he extracted his Hubble time, how he extracted the age of the universe. So you can see from the straight line fit, you can learn, interpret a lot of information. This is a typical way in which the relationship between the velocity of the receding galaxies and the distances to the receding galaxies is plotted. So typically, we plot as the vertical axis, so say the dependent variable, the distance to the galaxy, and we plot as the horizontal axis, the so say the independent variable, the velocity of the galaxy. And actually, it's typically plotted not the velocity, but rather a proxy for the velocity, which is the Doppler shift, the redshift of the galaxy, the fractional redshift of the light from the galaxy. Fractional redshift of light from the galaxy, as long as the galaxy is not approaching sort of the speed of light, recession from us. The approximate redshift, fractional redshift, is just the speed of the galaxy divided by the speed of light. So this horizontal axis here is really kind of V over C for galaxies, so long as they're not receding from us at large fractions of the speed of light. And so this is a typical Hubble plot. It's the normal way that the distances and velocities are plotted. In this way of plotting it, with the vertical axis being the distance and the horizontal axis being the velocity, or this proxy for the velocity, then the slope of the graph is actually the inverse of the Hubble constant, not the Hubble constant. Actually, it's the inverse of the Hubble constant times c, the speed of light. I've written it down here. Because we're plotting on the horizontal axis this proxy, the fractional redshift, which is V over C. Anyway, so I'm just saying there that the slope of this graph, the standard way it's plotted, is the inverse of the Hubble constant times C. What else did I want to say about that? That's a good question. I wanted to say that the original work used these Cepheid variables as standard candles for measuring the distances and the velocities of galaxies. That was limited by the brightness of the Cepheids, only enabled you to see relatively nearby, close by galaxies and measure their distances and their velocities. It was extended by the understanding of another sort of standard candle or calibrated candle that's available to astronomers, and that's what's well known now, that you can use supernovas. So you can use supernovas as standard candles to measure distances and velocities of galaxies. They're much brighter, and so that you can use them to measure distances to much more distant galaxies and the velocities of those distant galaxies. So it extends the data if you use supernova. It extends the data from the Cepheid variables. Okay, so we're going to go on to fit Hubble's data and from Cepheid variables, and also the extended data from supernova and Cepheid variables. We'll do that, and we're going to do it two ways. I mentioned this. We're going to do it by writing our own code to fit a straight line to data, distance versus velocity. And then we're going to use a library function to fit the data. We'll see how to use library functions to fit the data. In the future, we're focused on using library functions because they allow us to fit more complicated or sophisticated function. They allow us to handle the uncertainties in more complicated, sophisticated ways. But in today's class, we want to sort of see under the hood by writing our own code and then turn to using sort of well-established professional code. So this slide is to introduce the idea of a least squares fit to a set of data. So I'm imagining in this slide that we've collected some data that are XY points, like independent variable, dependent variable points that we have measured. So this might be, these distances and velocities of galaxies, or brightness of redshifts of galaxies. Those are a set of XY points, or dependent variable points. And so I've imagined 4 points here with the subscript 1, 2, and 3, and 4 labeling the 4 different points. And we want to these 4 points, I want to fit a straight line. And I want to find the best straight line through these data, the best straight line matching these data. So we've got to have a quantitative idea about what defines the best straight line. What is the best straight line for the data? Well, I put a few ideas here. Here's a sample straight line through our 4 data points. These vertical bars are the distances of the data points from the model, the straight line, at the location of the independent variables for the 4 data points. So these are the differences in Y for between the model and the measured data for point number 1, the difference in the model prediction for the data and the measured data for point 2, and so on for point 3 and point 4. That's what the vertical lines are. One scheme might be to say, well, we're going to try and minimize the sum of these differences. I'm going to call them residuals. They're kind of the residual between the measured value and the model value from the straight line. So we could say I'm going to try and minimize the residuals, the sum of the residuals. That would be the best straight line. But the problem with doing that is some residuals are positive and some residuals are negative, because sometimes the model is above the data point. sometimes it's below the data point. And so you'll have positive and negative residuals. And so the positive and negative residuals will cancel each other out. And it's not a very useful thing to minimize because the data, the fact that there's positive and negative residuals will kind of cancel it out anyway. So that leads you to, well, maybe as an alternative, I could minimize not the sum of the residuals, but the sum of the absolute sizes of the residuals. So that would be another procedure. You could do that. That would get rid of the problem of them being positive and negative residuals. But using the absolute size is kind of mathematically and theoretically awkward for minimizing. So we don't do that either. What we do is we minimize this sum of the squares of the residuals. So each of these is a residual. We would square it up, and the best straight line would minimize the sum of the squares of those residuals. And so that's what a least squares fit is to the straight line. Here's the formula for it. So this quantity here, the chi-squared, is the sum, it's the sum over the data points. So we've got the summation here of the squares of the residuals. Inside the summation, it is the square of the residuals for each of the data point. And the residuals, remember, is the difference between the measured value, yi, for each data point, and the predicted value, the model value, that's the f of xi that I've written here. So this is what we want to minimize. This just shows you on the left-hand side here, kind of the landscape of chi-squared, or how to imagine chi-squared as a function of the parameters of the model. If we're fitting a straight line, this function has two parameters. This function is a straight line, so like y equals mf plus c. It has a slope, we'll call it m. It has an offset, we call it c. So you can think of the chi-squared, the value of the chi-squared being a function of, it's a function of m and c, the slope and the intercept. And so it is a function, but it's not a function of the data points, right? The xi's, the yi's, they're fixed. They've been measured in what it's a function of. What's a smoothly varying function of is the slope parameter m and the offset parameter c. And so here I kind of imagine that landscape. This is the landscape of slope m horizontally, offset c vertically, and the color coding is the value of chi-squared. Here in dark blue, at the center of this dark blue oval, that's the minimum value of chi-squared. And then as we walk sort of up towards the right or down towards the left, we're walking up the walls of a valley to higher and higher values of chi-squared. And so the value of chi-squared here at the minimum defines the best value of m and the best value of c, the best value of slope and intercept to fit our data. And that's what we want to find. We want to minimize chi-squared and find the values of m and c that correspond to that minimum chi-squared. So that's our task. Okay, so here's how you might do that. This is starting with that idea of we're going to minimize a chi-squared. Starting with the idea that the chi-squared is calculated from your measured data, your xi's, yi's, and that the chi-squared is going to be a function, a smooth function of the model parameters, m and c, the slope and the intercept. Starting from that, we're calculating what are the best values of m and c. Based on those are the values at m and c, where the chi-squared is a minimum. So this just outlines how you do that. We're starting from the definition right upstairs here of chi-squared. I put in the actual function, right? The straight line function that is y equals mx plus c. So I plug that in here. That to find the minimum, right? This is a function in a two-dimensional space of two parameters, m and c. At the minimum, at the bottom of that valley, the differential of this function, chi squared, with respect to each of the parameters, the differential with respect to n, the differential with respect to c, will be zero. That's the meaning of the minimum. And so two equations that we can write down are if we differentiate with respect to the slope, that's what I did here. So I just differentiated this little guy with respect to the slope. Here, the n is the variable, right? And so I just use the regular rules of differential for this. Here's the function. Now I'm going to think in this third line here. This is a differential with respect to the offset, c. Now I'm thinking of c being the variable. And so I carry out those two differentials, which is what I've done upstairs, downstairs there, and I set them equal to zero, because that will define the minimum. So these are two equations that I can use. And this is one way I could write those equations. Another way I could write that pair of equations is as a matrix with a linear algebra is this matrix arrangement here. So this matrix equation here, if you think of the multiplication of this column vector with the top row of this matrix, that gives this top equation upstairs here. It's this equation here. And if you think of the multiplication of this column vector with the bottom row of the matrix, that gives this equation here. And so this is the matrix form of this equation. Okay. So given this, you can rearrange to solve, we want to solve for this. So if I was to multiply through by the inverse of this matrix here, then I could solve for this column vector here. And that's what this final step is here. So this is one way that we can find the best values of the slope and the intercept is to calculate them with this equation here. And if you look at just, we walk through the derivation. So the basic idea of the derivation was you want to find the value of m and c at the minimum. At the minimum, the slope with respect to m and slope with respect to c is zero. You use that information to create equations. You put those two equations together and you get an equation for m and an equation for c. On the right-hand side, it's just functions of the data. So it's functions of the dependent variable and the independent variable and the squares of those, or the products of those variables. So you see the xi's, you see the yi's, you see products of the dependent and independent variables, and you see squares of xi's, and the number of data points here. So this is the solution for the best straight line through the data. Yes.
Can we write down what m is, or that is not very important?
What m is, the value of m. The value of m is, well, we're going to calculate it. So on the next, let me go to the next slide. I think I'm going to answer it. No, actually, I'm not. I mean, this is sufficient to calculate it, right?
Yeah.
Because
But it's just when it's defined that way, I'm just wondering, I cannot see right away why m transpose n is that, and then m transpose y vector is the vector on the right hand side. Like what m will satisfy that, I cannot see right away.
yeah,
But then I know we can calculate m.
yeah. I think I don't know how to answer that question because I can't look at this and get some. I think you're asking for some intuition. Are you? Well, why does M look at this like this, and why does C look like this equation?
It's
Or-
more like, why don't we just say, oh, we calculate the inverse of that matrix, but instead we call it M transpose M. That's my question.
Oh, you mean this thing at the bottom? Okay, so yeah, so for the moment, ignore that. I'm going to come back to this.
Okay.
Yeah. Sorry, that's confusing that I put that there. I'm going to because I'm going to show you how we get this equation, which is what we're going to use in a slide or two. Okay, so the point here is that based on the data, you can calculate, and with, for example, these sets of equations, you could calculate the best value of C and the best value of M that go through your data points. If you want to calculate I put this slide in just for a bit of completeness here. I've given you the equations for the best M and the best C. How about the uncertainties on the values of M and the values of C? Well, if your data has uncertainties, then they will get reflected in uncertainties on the slope and the intercept. They'll be related to the uncertainties on the slope and the intercept. So that's all this slide lays out, really. Upstairs here, I'm calculating the uncertainty on the data based on the size of these residuals. So sum of the square of the residuals. So that's how I might characterize the uncertainties on the data. And then in this second and third equations, I'm propagating those uncertainties on the data points through to the uncertainties on the slope and the intercept with these equations here. And then finally down here, this sigma subscript MC, this is measures the correlation between the values of M and C that you extract. And so this is how you would propagate the uncertainties, measure the uncertainties of data, propagate those to uncertainties in the slope and uncertainties in the intercept, and the correlations between the slope and the intercept. And as you see, again, you can calculate sigma M, the uncertainty on the slope. You can calculate sigma C, the uncertainty on the offset. You can calculate the correlation between M and C. Again, just through these sums involving the data points, involving sums of xi, sums of yi, and products and squares of those xi's and yi's. So that's all that is on the right-hand side here. Okay, this is how we're going to implement that equation for the best values of M and C in our Python code. So this is how I've implemented it in the Python code I'm going to show you. And it just takes advantage again of the kind of possibilities within NumPy for defining vectors and matrices and doing algebra with vectors and matrices. So, and I think this will answer your question about what was the meaning of that M transpose M. So the way I'm gonna, in Python, solve for the slope and the intercept and the straight line fit to some data that we imagine that we measured is to introduce some matrix and vector representation of the data and the problem that we're trying to solve. So just walking from the left to the right here, I'm introducing two vectors and a matrix. So there's one vector that I'm introducing, which is a vector just containing the values of the dependent variables. So the yi's, y1 through yn. So it's just the column vector of the dependent variable data point. So maybe that's the in the Hubble plot, that would be the distances in megaparsecs to the galaxies. There's a matrix, that's this quantity here. It's actually called a van der Waals matrix. And this matrix will contain the independent variables. So it contains the xi's, that would be like in the Hubble plot, the horizontal axis. So it's the recession velocity, or the proxy for the recession velocity of the galaxies. So this matrix contains the xi's from x1 to xn, but it's organized in the following way. The first column of a van der Waals matrix would be the values of xi to the power 0. The next one, xi to the power 1. The next column, xi to the power squared. Next one, xi's cubed, and so on and so forth. That's the structure of this matrix. It's basically each row, starting from the left, going towards the right, is an increasing power of the variable, the independent variable in that case. So that's the pattern you see here. Now, you would have as many columns as the polynomial that you want to fit to the data. We're just fitting a polynomial, a straight line to the data. So we just got the highest term in the polynomials, order 1. And so we just got a column vector of 1s, which correspond to the xi's to the power 0, column vector of the xi's themselves. If we're going to fit a quadratic to the data, we'd have another column, a third column on the right, that would be the squares of the xi. But we're just doing a straight line fit. So that's how you build this graph. And then finally, there's a 2-element vector. It's called beta here. This just contains the parameters that we want to extract from the data. We want to extract a slope, we want to extract an intercept. And so we want M and C, and they are packaged up in this parameter beta, this vector beta, which contains all the quantities we're going to derive from the data. Let me remark that, well, it's obviously you want to create a vector yi that just contains all the dependent variables. This product of the matrix and beta, if you think about that product x beta, that is a column vector of all the mx plus c's for all the values of the dependent variable. So kind of think of the y and the x beta as being the left and right hand sides of this relationship between the dependent and independent variables. Recognizing that, a chi-squared is defined by this sort of matrix equation here. So the chi-squared, remember, was the sum of the squares of the residuals for your data points. Inside parentheses here, we're calculating the residuals. So the difference between the dependent variable and the function. So that here's the dependent variables in the y, and the x beta that contains the independent variable, and the model values for m and c. So this is the sort of model over here on the right of the parentheses, and this is the data over here on the left of the parentheses. And the difference between them is the residuals. The difference here is we don't have a summation, because the summation is really within the fact that these items are matrices themselves. We also don't have a square. Rather than a square, I've got the product of this matrix with its transpose. That's equivalent to the square. So it's just a different way of writing the chi-squared. You can now at this point, a couple of slides ago, we said, well, what are the best values of M and C? We said the way to find them is to they correspond to where this quantity chi-squared is a minimum. So let's differentiate with respect to M and C. The equations that we get from differentiating with respect to M and C, let's solve them for M and C. That's what we did. You can do the same thing in this language. In this language, we would want to differentiate with respect to beta to find the and set that differential with respect to beta to be set that equal to 0, and then solve that for the value of beta, and the value of beta contains the slope and the intercept. So that's kind of the world. You know about ordinary calculus, you know about vector calculus, but differentiating this matrix equation with respect to beta, that's matrix calculus. So maybe you didn't think about it, didn't want to think about it. But this kind of ordinary calculus, then there's vector calculus with vectors, but there's also matrix calculus with matrices. To solve for beta, you would use matrix calculus. Basically, you would say that, well, look, chi-squared is a function of the matrix beta. If I differentiate with respect to the matrix beta and set that equal to 0, that locates the minimum value of chi-squared. And then that equation that emerges from differentiating chi-squared with respect to beta and setting it equal to 0 can be solved for beta. And if you solve it for beta, you get this equation here. This equation here, if you think about it, the yi is where the dependent variable lives. This is a vector of the dependent variables, and the x's and the transpose x's and the inverse of the product of the transpose of x and x. That's where the independent variables live. So the data is over here on the right-hand side, and it's just a way of calculating the best values of M and C, which are the two elements of beta, from the data that you have, your xi's and your yi's. So I'm not showing you how you do that, but I did put it, and I'm not going to go through it. I did put it on the next slide. This is matrix calculus to solve the problem in this particular form. So maybe that answers your question, where it came from. It's also handy because we talked about the uncertainty on the parameters. Sigma m, sigma c are the standard deviations. There's squares of the variances on those uncertainties, and sigma mc are the correlations between the two parameters. Well, they're easy to calculate in this particular language. So you can calculate this 2x2 matrix, which contains the uncertainties and the correlations, by this equation here, which again involves these vectors and matrices that we've created, and here the uncertainties on the data points. So this is a very handy way for solving a straight line least squares fit to data in, for example, Python, where you've got NumPy and you can handle the manipulation of these matrices very straightforwardly with NumPy functions, and that's what we're going to do. So I'm gonna use this equation to do my straight line fit, and I'm going to use this equation to calculate the uncertainties on the parameters and how they're correlated. As I say, if you wanted to extend this from a linear straight lines fit to a quadratic fit or a cubic fit or whatever order of polynomial fit that you're interested in. It's a matter of extending this van der Waals matrix. If you want a quadratic fit, you just get a third column with the squares of the dependent variables. And if you want a cubic fit, you just get a additional fourth column with the cubes of the values of the independent variables. You would then, if you went through this procedure, you would find that your beta, if you're doing a quadratic fit, it's just going to have three parameters in it. It's going to have the offset, the slope, and the slope of the slope. And so this would be a three-element vector here. If it was a fit to a cubic, then this would be a four-element vector with the best values for the coefficients of all the terms in that cubic polynomial, the offset, the slope, and so on and so forth. So this procedure, we're just going to write it down for a linear straight line fit, but it would be easy for you to extend it to a quadratic or a cubic. As I say, I just put in here how you actually do that matrix calculus to starting from the chi-squared as a function of the matrix beta, find out what the values of beta are in terms of the distance. So these are the steps you go through. And I also put in, if you want to at some point imagine, we've got a lot of matrices here, matrices of the dependent variables, independent variables, and combinations of them. I've just written them out explicitly. Here's the matrix X, will meet its transpose. Here's its transpose. We'll meet the product of the matrix X and the data. I've written out that. We'll meet other products like X and its transpose. The inverse of X and its transpose. So I kind of wrote them all explicitly in terms of the individual data points themselves, just as a record. Okay, I'm going to go to the code. When we go to the code, I'm going to want to take products of matrices, and I'm going to want to find the inverse of a matrix. So I'm going to use NumPy's linear algebra for that. So I'm going to use a function dot, which is how I'm going to multiply matrices together. I'm going to use a function inverse, which will give me the inverse of a matrix. I'm going to use a method transpose, which will give me the transpose of a matrix. So in the code, look out for inverse, look out for dot, look out for transpose, because those are the three things I have to do that I've kind of enumerated to calculate the best fit parameters. I'm going to need to take a transpose of a matrix, take the inverse of a matrix, and take the products of matrices and vectors. Yeah, let's go to the code. So here's my code. First cell, I just got the usual importing of NumPy, because I'm going to work with vectors and matrices and products and inverses of them. We use NumPy. Importing matplotlib because we're going to plot the data and look at the data, so I need that. But I'm also importing this package, this library. It's actually a module within SciPy. And I'm going to import that because I'm going to do my least squares fit using the equations that we laid out. But I'm also going to compare my results to kind of professional level least squares fitting package. And I'm going to get that out of this library here. So I'm importing that as fit, and we're going to use functions in this module here. I also, I'm going to be fitting data. I'm going to be got hold of Hubble's old data, and I'm going to be fitting his old data on Cepheid variables. And then I actually got hold of extended version of the data that includes supernova data, and we can fit that too. And so I've got those on my Google Drive. I think I've also put them. This is not the fitted problem you work on in the assignment, but I did put them in the in our canvas directories. Okay, so that's the first cell. Second cell, I'm just grabbing the data and I'm going to just plot the data so we can take a look at it. So I got two files on my drive. One is the Cepheid variable data. It's in this file name that's called Hubble low Z data. So remember Z is the fractional redshift, and it's a proxy for the recession velocity of the galaxies. The fractional redshift times C is the recession velocities of the galaxies. These are galaxies with low recession velocities because they're nearby. These are nearby galaxies because these are the ones that could be seen with Cepheid variables. There's a second file that is just called Hubble data, not low Z Hubble data, that has the Cepheid variables in it, but it also has the supernova data in it, which means that it has galaxies that are more distant, recession velocities that are larger, that are observable with the supernovas that are much brighter and can't be seen with the Cepheid variables that are not as bright. Anyway, right now I'm reading this, going to read this Hubble's data from the low Z file. And I happen to read it with a function in NumPy. It's low text. It's a simple function that you can use to read data that is just in the form of columns of numbers. It's not a function that can handle more spreadsheet-like data, database data where you've got headers, more complex formats of the data. But the data I had was in very simple format. It was just the two columns of the distance to the stars and the redshift of the starlight. So I read in the data into Hubble data. It's going to be an array with two columns. I'll slice out the first column as another X variable. The slice out the second column, my Y variable. The X variable is going to be the redshift. Maybe I should have given it a different name. The Y variable is going to be the distance. And then I'm just going to plot the data so we can take a look at it. So this is the data. Here's X, it's the fractional redshift. Remember, if we multiply this by speed of light, that is the recession velocity. Vertically, this is the distance of the galaxy. We got it from the brightness, but it's the distance in units of megaparsecs. So this is typical Hubble data. Here we have 18 data points that go out to redshifts of 0.1. And these are the data that we want to fit to a straight line. Now, obviously, they look like they follow a straight line with some fluctuations, statistical fluctuations that are related to the ability to measure the quantities and maybe also related to true proportionality between brightness and distance and redshift and velocity. So here's our data. This cell is where I'm going to calculate the best fit line to the data. So the slope and the intercept of the best fit line to the data. Better make this larger. Using that matrix algebra equation that we derived from matrix calculus. So I've got to create some vectors, and then I've got to carry out some products of vectors and so on and so forth. So I already had the vectors X and Y when I read the data in. We needed the column vector that had the dependent variable in it. We needed a van der Waals matrix built out of the dependent variable. So that's the first line here. So it's kind of the input into this calculation is coming from the XY points. One of the ways we represent the variables is with for the independent variable is just the column vector, and then for the dependent variable we need a van der Waals matrix, and I haven't got that yet, so I'm making it here. If you remember that matrix, if you're doing a linear fit, the left-hand column is just a column of ones for however many data points you got, and then the right-hand column is just a column of the x1, x2, and 3, so on, up to xn. And so that's what I'm building here. I'm building it with this non-p-fact function here, column stack. It just builds a matrix out of, I mean, it says what it does. It stacks columns. It literally stacks columns into a matrix. Inside the argument are the columns that you want to stack into the matrix. I'm stacking a column of ones, of n, uppercase n ones, next to, on the left-hand side, of a column of the x values, of n x values. So that's making that matrix. So now we've got, in the language of the slides that I showed you, we've got the vector y, and we've got the matrix x that contain the dependent and independent variables. And then we had that calculation to perform. Here I've written it down here, except just confusingly. I called this matrix n here, and we called it x in my slides. It contains the dependent variable, independent variable. So in my slides, all the m's are actually x's. This is how we're going to calculate beta. It's the transpose of m is the inverse of the product of the transpose of m and n, multiplied by the transpose of m and the column vector y. So this is what we've got to do. So we've got to build this up in parts, and that's what I do in these next 4 lines. This line here calculates the product of the transpose of M and the matrix M itself. And I'm doing that with, so to take this as a product of 2 matrices, I'm using dot to calculate the product of 2 matrices. The arguments of the 2 matrices, one is M and one is the transpose of M. I'm using this method, matrix method, to calculate the transpose of M from M. So this is M transpose M. I want the inverse of that. And here we have this thing. We want the inverse of that. And so I've got to calculate the inverse of that. So I'm going to use this other function I mentioned, which is inverse, which will calculate the inverse of a matrix. The argument of that is just the matrix we want to calculate the inverse of. So I'm given the function inverse, this matrix from the previous line, and it's going to give me the inverse of this product of M transpose M. So now I've got this one. Now I want this piece here. Well, if I want this quantity here, this is the product. I'm going to use dot again of the transpose of the matrix M, and then this vector that contains the dependent variable. And so I'm going to use dot, again, the function dot for that product. Here's the first term in the product, the transpose of the matrix M. Here's the second quantity in the product. This is the vector Y. And so I calculate MTY, I called it. So that's calculated that term here. And then finally, I've got to multiply this first term upstairs against this second term in parentheses upstairs here. So I need this product. Again, I'm using dot for that to accomplish that. And now I've got a, call it beta here. It's going to be a matrix that contains the two parameters. And so that's implementing this formula we derived using matrix algebra and matrix calculus that will contain now the best values of the slope and the intercept as determined by the parameters of our data, the dependent and independent variables. So now I've got the best parameters. And let's just take a look at that. In the print statement, I just wanted to show you what the matrix M looks like, what its transpose looks like, and what the various things that we build out of it look like. So we're going to build the product of the matrix M times Y, the product of the transpose of the matrix M times M. We're going to build all these different things here, and I'll just show you. So this first bit here, this is the matrix M. Remember, this is the van der Waals matrix. Its left-hand column is a bunch of ones, and its right-hand column is the independent variable to the first power. And so this is just the fractional redshifts in this second column. So that's M. This is the transpose of M. We're just interchanging the rows and the columns. And so now we got a row of ones. That's the top row of the matrix. And then we got the second row of the matrix is the redshifts, fractional redshifts. This is a typo. This should be, this is significant typo. Let me go back upstairs. I'm failing to do this now. I'm printing out MTY is the transpose of M times the vector Y. And then I'm plotting M T, the transpose of M times M. So this is a little column vector, which is made from the product of the transpose of M and Y. The transpose of M, remember that was a wide, had lots of columns, but it had just had two rows. And Y is just one long column. So when you multiply those two together, you just get this two-element array here. This is the product of the matrix M and its transpose is just going to be a 2x2 symmetric matrix. Here's what that looks like. You see it is symmetric. The inverse of that will also be the inverse of a 2 by 2 matrix is the 2 by 2 matrix. Here it is, and again, it's symmetric. And then finally, I'm printing here the results of the calculation. This is the what we called it in my slides beta, but this is the array that contains the best values of M and C. That's the two elements here. So this is the best value of C. This is the best value of M. Okay, so let's printed out all that detail there. I did calculate a few more things down here. YF. YF is the model values of the dependent variable at the location of the independent variable measurements. So this is mx plus c, but with the model values for the best fit model values for the two parameters. If I take the difference between YF, that's the Y calculated with the best fit function, and the data itself, that's the array Y, these are the residuals. This is the difference between the model and the data itself. I can calculate the chi-squared of the residuals by just squaring up the residuals and summing all those terms. That is the chi-squared. So here's the chi-squared. And what we call the variance is the chi-squared divided by the number of degrees of freedom. And this reflects the typical uncertainties on the data points, the different between the model and the data points. This number that we divide by is the number of data points less the number of parameters in your model. So we had n data points. We have two parameters, the slope and the intercept in the model. So we divide by this number of degrees of freedom, which is the difference between them. This is how I can calculate the uncertainties on M, the slope, or C, the offset, and then correlation. This is how you calculate it. This was the second of the formulas that we mentioned in the slides. Okay, so I calculate these things, and then if we go down here, we get rid of all the printout of the matrices. So here's the plot of the data again. We already plotted out the data, but I've added to it now this best fit line. Once I've got the slope, once I got the intercept, I calculated YF, which is the best line through the data. And so this looks like a very reasonable line through that data. We see that some points are above the line, some points below the line, and it seems to follow the trend of the data. So we did do this calculation of the least squares straight line through the data. I also plotted out some of the numbers that we extracted. We met before the slope and the offset. So let me make this larger. Here's the slope, here's the offset. These are the two elements in that. I called it chars here, or beta in the text. This two element vector. These are the uncertainties of them. And by propagating those uncertainties using that covariance matrix, this is the chi-squared for degree of freedom. Again, this is reflecting the sort of differences between the model and the data. the residuals between the model and the data. If you remember, the slope of this plot, because we plotted distance vertically versus redshift horizontally, that isn't, the slope isn't the Hubble constant. The Hubble constant is 1 over the slope times the speed of light, c over the slope. And so I calculated the Hubble constant, and it should be per parsec there. We said it was about 70 kilometers per second per megaparsec. So my fit came out to be 67 kilometers per second per megaparsec. We said that if you convert that into a time, so the Hubble constant has units of inverse time. If you take the inverse of the Hubble constant, that's a time. That is the age of the universe. If you do that procedure, right, this is kilometers per second per megaparsec. You would have to put the kilometers and the megaparsecs in the same units. So you would have to convert them into meters or whatever, or convert the kilometers into megaparsecs or the megaparsecs into kilometers. So you'd have to do that. You also have to I converted the seconds into billions of years. So I needed that number too. So there's a few unit conversions that went on here. But if you do the unit conversions, you get a time that is 14.5 billion years. So about the 14 billion year age of the universe. So we've just fit Hubble's data, and we've got out the Hubble constant. We got out the age of the universe in the same way that he did. So that's with our unfitting routine. This cell down here, I wanted to show you how to use a library fitting routine. So this is, we imported this library package fit. It contains a function curve fit that you can use to fit the data. So when you call curve fit, you call it with the arguments that are obvious. So you've got to call it with your array of independent and dependent variables. That's the X and Y here. You also call it with the name of a function. So the name of the function is this first variable here. And that function is a function that defines the function that you're fitting to the data. So I've made a user function called func that I'm passing to curve fit, the library function. My user function has arguments where for the independent variable and the parameters of the function, that's the P0 and P1, and it defines a function which is a straight line, which is a linear fit. And so when I'm calling curve fit here, I'm calling it not only with the data, which is obvious, but it's also obvious too, you've got to tell it what the function is. The way you tell it what the function you want to fit is by defining a user function. Embodies that function that describes that function you want to fit. Here, calling curve fit with these arguments performs the fit. Does the least squares fit, and it returns 2 arguments. The first argument that it returns, the left-hand side of the comma, is called it pars because it contains the parameters of the fit. So in this case, there's 2 parameters in the fit, so it contains the slope and the intercept. The second argument contains the matrices of uncertainties associated with the fit. So it will contain the uncertainties on M, the uncertainties on C, and the correlation between the two. So they're all embedded in this covariance. I also, after calling the function and got the best fit parameters, I calculated the model values of Y for each of my data points. So this is the model prediction. This is the residuals, the differences between the model prediction and the data itself. This is the chi-squared and the variance that we calculated before. So we can take a look at this result. Which is here. So these are now the results from the curve fit function, again in magenta now, the same data points, same axes. This is the best fit straight line from the curve theta gave me, curve fit gave me. And again, it looks like it's a very reasonable straight line with points above and below the line itself. Here are the parameters for the slope and the offset. And here's the chi-squared. Here's the value of the Hubble constant that I've extracted. Again, this is the units here, right? It should be kilometers per second megaparsec. And here's the age of the universe that I've extracted. We might compare those with our own calculation, our hand calculation. And I think they're essentially the same. Look, the slope, 4448.86. And 4448.86.